welcome to this calculus tutorial. Be sure to pause and rewind whenever you need to in order to get the most out of this video. So we are going to solve this optimization problem. I wrote that word up here so we can remember that it's an actual optimization problem. So we have 1.5 million square feet, and that's the area that we have. And we're going to enclose that in a rectangular field and then divide it in half with an extra fence. And our farmer wants to do this to minimize the cost of our fence. So let's jot down some notes to ourselves. Our area, we know, is going to be 1.5 million square feet, which I can write that then as 1,500,000. So we'll go ahead and jot this down here as feet squared. Then I can go ahead and come up with my fencing, and my fencing is the one that I want to minimize. And so whenever I am minimizing, let's see here, make sure I get that written. So whichever one I'm asked to minimize or maximize, that's the one I'm optimizing. So in general, we call these optimization problems. So now it's always helpful, in my opinion, to draw some sort of picture so we can get an idea of what's going on. So it's a rectangular field and then split in half with an extra fence parallel to one of the sides. So let's label the long sides as Y and the short sides as X. And now let's start coming up with some equations. So for area, the area of our rectangle is simply X times Y. And we know that that's equal to our 1,500,000 feet squared. And then we know our fencing, this is the total length of fencing, is going to be 2Y plus 3X, because that's how much fencing we have. Now, if I want to take this area and I want to solve it for Y, all I have to do is I move the X over to the other side. And the reason I'm doing that is because the F, the fencing, is the equation that I'm going to optimize. So this is the one that I'm going to take the derivative of. But before I can do that, I need to get it down to just one variable. And the way that I do that is I plug this now into my fencing equation, which will simplify it. It will get it down to just one variable. In this case, it will get it down to just X. So when I do this, I end up plugging in my 1.5 million square feet over then my X, and I take that plus my 3X and I simplify. So what I end up having is 3 million divided by X plus 3X. And now we can go ahead and we can take the derivative. So my F prime, the derivative of this, ends up being 3 million divided by X squared. But remember, that'll have a negative out front. And then we'll go ahead and have our plus 3 because the derivative of 3X is 3. So now what happens in these optimization problems is I set the derivative equal to 0. So I go ahead and I plug in 0 for F prime and I solve this. When I rearrange things and I solve, I end up getting an X of 1,000 feet. Now, don't forget to take the square root at the end because this is an X squared. So this is already one of the dimensions. This will be my short side of my rectangle. Now, in order to get the Y variable or the dimension of the long side, I simply plug in that 1,000 into my original equation up here. And when I do that, I end up getting a Y of 1,500 feet. And so I have my dimensions here. To answer the problem, I can draw another picture and I can label what I know. The long side we said was 1,500 feet. And the short sides then will be 1,000 feet. And by doing so, I will have minimized the amount of fencing, which then minimizes the cost of the fence, but still giving us an area of 1.5 million square feet. So I hope this helps. Find some other optimization problems similar to this and follow the same strategy to solve those. Good luck!